Okay, so we're done one unit. Time for second unit. They're actually really closely related to some degree. First unit, I decided to work on just the stuff that I could consider a polynomial function. Even before we move on to the non-polynomial functions, let's do a quick recap of what makes something a polynomial. Anyone want to volunteer a definition of a polynomial? Sure, that'll work. Let's start with that. Polynomials have terms. For example, this is polynomial. It's got an x to the 3. Or something that goes x to the 2 could be polynomial. Or even x to the 1 could be polynomial. And you can throw all of those together, and you could have even a polynomial that goes x to the 5 plus 3x squared minus 2x plus 1. That makes something polynomial. That makes sense? Pretty much that's it. Like that's the definition of a polynomial function. In that unit, then, I threw in a few of the other little random topics that are kind of important, like the f of g of x kind of concept, or the f plus g of x concept. We also talked a little bit about how if you do like f of 2x, it takes the graph and squishes it in. Well, a lot of those same concepts that we kind of worked with around polynomial functions, we're still going to use those, except now we're going to do things that are not polynomials. And so the three main things that we're going to focus on in the non-polynomial function unit are going to be square roots. If something's a square root, it's no longer considered polynomial. We're going to spend a lot more time working on things that have fractions, because those are not considered polynomial anymore. And then we're going to branch off into exponents and logarithms. And so that would be a graph where, you know how like here you have x squared, and the 2, like the actual number, is the exponent, and the variable is the number below it? We're going to talk about a graph where 2 is the base.
Mr. Forrester, can you please come to the office? Mr. Forrester, please come to the office.
So, 3 main sections to this unit. Square roots is where we're going to start. Then we're going to go into fractions and deal with rationals for a little bit. And then after that, we'll deal with like exponents, and the opposite of an exponent is a logarithm. Does that make sense? A lot of the same principles that we did before are still going to apply though. Okay? So for example, if I were to give you 2 and then make it a 2x up here in the corner, what would that do to a graph? Squish it in. Yeah, because a 2 in front of the x means that it's like f of 2x. What you've done is wherever you used to have an x right here, there's now a 2x there. So it makes everything squished in. What was that?
What if it was like a half?
A 1/2 would pull it out then.
Okay, so the same rules apply.
The same rules apply. So a lot of the same things we've been doing, we'll keep doing, except now we're going to introduce some strange new graphs to them. So I'd say, for the most part, what we're going to do is we're going to talk about what the graphs of these functions look like. We're going to talk about properties of them, like things domain, range, asymptotes, x-intercepts, y-intercepts. We're going to talk about all those sorts of different things, only now the graphs that we get are going to be strange and weird looking. I mean, not that they weren't starting to get there anyways. Does that make sense? So I started off with just a basic slide here then, talking about different functions we've learned about. Constant functions. This is a linear one, I guess. That's quadratic, that's cubic. All of these guys right here would be considered polynomials. Polynomials have to be written something like this. Okay. Whereas these ones that I'm working on here on the next little bit here, you guys already learned absolute value last year with me a little bit. Today we're going to focus on this one, the square root function. So let's start on that. Before we get to square roots, though, I want to do a quick bit of review from last year on how square roots work, just the terminology. So let's say that I gave you the third root of 7. This 3 right here, we call that the index. It just lets you know what type of root you're looking for. The stuff under the square root sign is called the radicand. Let's say it wasn't the third root of 7, though. Let's say it was the third root of 8. Anybody know what the third root of 8 is? It's 2. And the reason why is that 8 can really be written as 2 times 2 times 2. And if you have something 3 times, then you can cube root it. That makes sense. Whereas if I asked you for the square root of 9, the square root of 9 is really equal to 3 times 3. In a way, you could then say that that's equal to 3 squared. And then what happens is that this square root sign and this square root sign, they're kind of opposites of each other, so they cancel. That's kind of the logic behind how square roots and cube roots and stuff works. So far, so good? Moving on. Except I lost the stupid little writing cursor thing. Where is it? There, I'm going to just go down here. Okay, another thing we would have talked about last year is the idea of how you can combine square roots, like how properly to put them together. If I gave you a 5 root 7 and a negative 7 root 7, negative root 7, those guys can go together because they have the exact same radicand. Exactly. Yeah, you can't put them together unless they are literally the exact same. So x is not the same as y, so you can't put them together. So like here, this is a 5, that's a 3, they can't go together. Or here, this is a 4th root of 5a, this is a 5th root of 5a, same thing, they're not the same. But here I have a 3rd root of 5x squared. Here I have a 3rd root of 5x squared. They can go together. Are these kind of things you recall from last year? It's actually what I'm doing with my grade 11s right now. So here's another concept that may come up, the idea of mixed radicals and entire radicals. These numbers are equivalent to each other. 3 root 2 is the same as root 18. And hopefully you have a little bit of remembrance of how you can convert the two. Let me start with the mixed radical. With the mixed radical of 3 root 2, what you can do is you can take that 3 from the outside, and you can put 2 of them on the inside. Is there called doing that at all? The idea of like take the outside number, shove it inside the square root sign, but you got to put it in there twice. So then 3 times 3 is 9 times 2 is 18. Or working backwards, if I give you a root 18, I would recommend break it up into a number that is a perfect square, like say 4, 9, 16, 25, 36. Something that can actually square root. So in this case, 9 and 2. And then the reason I picked 9 and 2 is that 9 can actually square root to 3. I wouldn't recommend making this a 6 and a 3. Yes, 18 does equal 6 and 3 multiplied, right? But why do I not choose those? Because you can't actually square root 6 or 3. So far, so good. Let's just do a practice slide. You guys want to try converting mixed to entire and entire back to mixed? Like, why don't I do 2 of them and give you guys the rest? So like, here's a 4 root 7. Take the 4, shove it inside the square root sign, but put it in there twice. So now you'd have a 4 and a 4 and a 7. So I need a calculator for this. Yeah.
You're putting it in there twice because
It's a square root. So when you guys do the cubed root a little bit later, put it in there 3 times. I can't do 16 times out of my head this early in the morning. 112. That make sense? And then the other way, if I have a root 50, I mean 50 is 5 times 10, but neither of those are helpful. 25 and 2 is though. Why did I pick 25 and 2? Well, because 25 can actually square root to become 5. Does that work? Okay, take like 2 minutes and try a couple more of these. This is not necessarily what we're doing. We just want to do a quick rehash of how square roots work though before we move on. just going to start throwing a few answers up here on the board. Just check your work against mine. I wasn't intending to spend all of my time today on this, but just make sure you have the idea. So. For this one right here with the negative 11 root 8, if you take negative 11 and shove it inside the square root sign twice, it actually makes it a positive. So you can probably skip the negative out front, but you could actually make it a plus or a minus square root, actually. I'm going to focus on that a little bit later. The idea that when you square root numbers, there's actually a positive and a negative square root of everything. What's that going to be? 9 times 5 will be 45. And squared. Oh, that's gross. So I gotta find perfect cube numbers that go into 432. Okay, 432. 8 works. But each work again though. So no, I'm gonna just do a factor tree. 432 was 8 and 54. 54 is 8 and 7? No, that's 56. 54 is 9 and 6. That's 2, that's 2, that's 2. That's 3, that's 3, that's 3, that's 2. So I've got 1, 2, 3, 1, 2, 3, 4. Okay, so I can take out a 2. And I can take out a 3, so I can take out 6 and leave behind a root 2. So that's a minus 6 cubed root of 2. Anybody else get that one for the minus 432 one?
Yeah.
You, by the way, could throw the negative out front. You can actually cube root a negative number, though. So you could have left the negative on the inside, actually, and made that a positive. Both of those would be valid ways of writing a cubed root. Anyways, do you guys feel like you have a hang of this? Okay, let's move on then. I don't want to spend all of our time on that. Those are just skills that are like background skills that could come up, but that's not the point of my lesson today. The point of my lesson today is I want to show you what a square root graph and a cube root graph look like, and then we're going to talk about how to move them around on the graph. So I want to do a table of values rather than our calculator to start, because I want to make a point behind some of the properties of this graph. So let's just pick some values for x to plug in. 1 is a great number to start with, only I'm going to leave a little gap for a number to go above it. But
0.
We'll do that one in a second. But 1's a great number, though. What happens when you square root 1?
It's smaller.
Actually, it technically stays at 1.
It's too early.
Yeah, 1 square roots to 1. Taylor, you mentioned 0. What happens when you square root 0? 0. Okay. I'm actually not going to pick 2. 2 is a number you could square root, but I'm not going to... It's not a fun number to square root because it gives you a decimal number. So I think the next most reasonable number that I should actually plug in for x would be 4, because that'll give me 2. And the next most reasonable number would be 9, and it gives me 3. Now, can you plug in 2? Sure, it just means you're going to get 1.4173, whatever that number is, right? Could you plug in 3.97234? Sure, you could square root that number. Which leads me to my first major point about square root graphs. There is a certain number that you cannot plug in. Actually, a whole group of numbers you cannot plug in. In fact, half of the numbers in the universe you can't plug in. You can't plug in negatives. Does that make sense where I'm leading here? So my first point I want to make is that, when we do domain and range, normally we say domain is like x is an element of the reals. That's not true anymore. The domain now is going to be x is greater than or equal to 0. That makes sense? If you like I like the vending machine analogy. This would be like saying you can plug in quarters, you can plug in loonies, you can plug in toonies, but this vending machine does not take American money. I don't know, American money in this analogy is the negatives, right? It's like, it will not work. You can try plugging it in and it's not valid. Makes sense? Okay, let's try plotting some of these points then. 0 would go with 0 right here. 1 would go with 1 right here. 4 would go with 2 right here. And 9 would go with 3. This graph looks like this. One of the unique properties of a square root graph right here is that it just starts. Like there's no asymptote, there's no hole in the graph. It just all of a sudden it just starts. I don't actually have like a name for that point, but like this point right here is kind of a key point. It's like the starting point of the graph, right? Does that make sense? Okay, let's talk about the range of this graph. If the domain is x is greater than 0, anyone have a stab at what the range is going to be?
Probably can't be negative.
That's true, right? I mean, can you square root a number? I mean, well, how about let's look at this. Let's look at our graph here. Do you have any numbers down here below the axis?
No.
Will you ever somehow get numbers below the axis? This graph does not like keep on going, right? That's not what's happening, right? The graph just literally starts at 0. It looks like it's going up, and it'll slowly but surely keep going up. Will it eventually hit the number 10? Like, will it eventually get this high up here?
Yeah.
Sure, it just means that you'll have to have x be 100, because then 100 square roots to give you 10.
There's just greater than 0.
Yeah, it's greater than equal to 0 then.
Well, yeah.
Okay, I want to start getting you guys more and more used to, though, a second way of doing notation for this. And I kind of threw a few examples in before. Here's another way you could write this. It would look like this. Square bracket, 0, comma, positive infinity, curl bracket. I've kind of shown you this notation a little bit already, but I want to explain it a lot more now. This is another way of writing this. Here's what this means. 0 is the lowest number you can use. Positive infinity is the highest number you can use. Now, infinity is not a number, but does that concept make sense though? Like it will go as low as 0 and as high as positive infinity. But I want to talk about the brackets. A square bracket means you can include 0. 0 is inclusive. However, because positive infinity is not actually a number, we use like a curled bracket to mean that it goes up to that high, but not including that number, because really, like, infinity is not actually a number. Come on in, unless it's locked, I guess. Might be locked. Is it locked? Sorry, guys. I'll come unlock it while we're doing this.
Tom, do you want yogurt?
This is the best yogurt, by the way. This is the best yogurt.
Yeah.
I really like the Activia yogurt. It's good.
Does that make sense? Okay, so then for range you can do the exact same thing. Y is the lowest number you can do is 0, and the highest number you can do is positive infinity. I've actually shown this to you before. I think on one of your assignments it said like 2 bracket 8. That's a fancy way of saying that x is less than 2 and or greater than 2 and less than 8.
What does the round bracket mean?
So the round bracket means that if I use the term inclusive and non-inclusive, would that terminology make sense? So like inclusive meaning that 0 is a number you can start with. But we always use a round bracket for positive infinity because infinity is not actually a number, it's more of like a concept. Like it just keeps going for forever. Okay, where were we before that? Does that make sense so far? So that one's our x squared graph, or no, cube root graph. Square root graph, my goodness gracious. Now let's do a cube root graph. So I'm going to maybe try to draw this on the other side. Sorry that it's already a bit of a mess on here. Let's do x and y, but let's do the cube root now. So give me some values that we can try to cube root. Honestly, 3 is probably not. I mean, 3 does cube root, but it's not a nice number.
You can name the 0.
We can do. Okay, so let's start with 0. Let's start there, and I'm going to throw it right in the middle because you made a good point. We can do negative numbers. 0 can cube root at 0, so that goes right in the middle here.
8.
8 works. I'll throw that way up here. 8 cube roots to 2. So way over here, 8 is a 2. Any other numbers that seem like good ideas? Okay, -8 will cube root to -2. 1 will cube root to 1. Let's throw some of those on here. -8 would be -2. There's one more that's probably worth doing. -1 would cube root to -1. Well, not necessarily an inverse. It's kind of like a cubic graph. You know how in our last unit we learned about how a cubic kind of does this shape to it? That's the shape of this graph, except it's sideways, which is like an inverse, like you said then, I guess. Yeah, I guess it's an inverse cubic graph. It's like this graph right here that we just did in the last unit, only you guys see how it's kind of sideways? Does that make sense? So real quick, let's talk about some properties of this graph. What's the domain? X can be anything. Here's another way of expressing that though, because I want you guys to be comfortable in case the diploma asks it in a different notation. You could write it as it can go from as low as -infinity to as high as +infinity. It's another way of writing it. You guys have probably picked up on the fact that like a large part of this year and going forward is notation. And just like knowing what different ways of writing stuff means. So range, same thing actually. You can have any y number you want. This graph here will slowly but surely keep going upwards. It might take forever, but it will slowly but surely go up, and this graph will slowly but surely make its way down. Like it'll get there. It'll just take its time. So far so good? Okay. Sean used the word inverse, and I kind of said you were wrong, but I don't know why I said that. These things are actually inverses of stuff that we've talked about before. Here is a quadratic graph right here. A square root graph is actually the inverse of a quadratic graph, with one exception. You don't get the bottom half of the graph. Do you guys remember me telling you a while back why we don't get the bottom half of the graph? Square roots can be plus and minus. And so we probably should get the bottom half of the graph, but we only ever include the top half, because otherwise it's no longer a function. That makes sense? A function has to be able to pass a vertical line test. And if we were to have included the bottom half of this thing right here, it would no longer actually be a function. So when we talk about square root graphs, we only talk about the top half right here. But it is actually an inverse. A square root and a squared graph are inverses. Therefore, a cubed root and a cubed graph are inverses. So good catch on noticing that. I don't know why I said whatever I said to you there. So here's another picture of the exact same thing. Does that make sense? Moving on. Let's make some changes here. So one of the things we learned in our first unit is that we can make some transformations to graphs by like timesing by 2, adding 3, throwing a negative sign in. And I wanted to make sure I was kind of clear about something here. It looks to me like the way I've written this is that it's the same graph twice. So to clearly make a point, I'd like to write it out here. I want to make the f of x graph be the square root of x, and then I want to add 2. Okay. Whereas for the g of x graph, yeah, I want the plus 2 to be inside the square root sign, just so that we can make that distinction clear. Does that make sense what I'm asking for here? So usually when I write it, just so that we're clear, what I would do for this one right here is I would put that in a little bracket there, and that would imply that all of the x plus 2 is under the square root sign. Whereas for this one right here, if I don't write a bracket, it means that we're only square rooting the x, and then we add 2. Yeah, well, like this one right here, this 2 at the end moves the graph up 2, right? So let's graph this thing. You used to just start this graph right on a dime here at 0. So now move it up 2. Now it's up here. It used to go through 1 and 1. Well, now that's up here. It used to go through 4 and 2. Now that's up here. No, that's too far up. Right there. And it used to go through 9 and 3. Now that's up here. So this is what that graph should look like. So we can still move graphs around even if they're not polynomials. So that's this one right here. Good. So then for the other one, it's going to move it over to here. And there. And there. And there. Like that. Easy enough? For sure.
It's just moving like 1 over?
2 over.
Oh.
The purple one is two backwards, basically. Okay, let's talk properties of the graph. Mainly domain and range. Anyone want to throw out the new notation I've been showing you? What would the new notation for the domain be for the red graph? Domain would be 0 to positive infinity. Because your x numbers for red go as low as 0. Inclusive 0, and then go for forever. Good. Square bracket 2. Positive infinity. Because you're starting as high as 2 now. That work? Brad, I think the one you were describing is the purple graph, probably. So then for the purple graph, your domain can go as low as -2 now. And goes up to positive infinity. And our range... That one for you guys. What's the range of the purple graph? Good job, guys. That's more or less it. Like, that's the skill I need to show you guys. I've introduced a new type of graph. And so, based on that, now we just need to prepare for any sort of question they throw at you. So they might ask you about its shape. They might ask you about domain and range. So here's a couple of... Actually, you know what? This slide right here, I think I just threw in just to remind you of all the different things you can do to a graph. If you throw an A value in front of it, it like pulls the graph up and down. If you throw a B value in here, it would like squish it in. If I threw an H in here, don't forget you still need to use brackets still. That would move it like side to side, and this would move it up and down. So now that I've shown you the basic concept, we just need to, I don't know, solve some different questions. So without using our graphing calculator, let's see that we can kind of sketch what this would look like. What does a normal square root graph look like? Well, it looks like, I don't know, roughly this. So in purple, here's a regular looking graph. Now let's move it around. What do I do first? What does a negative do? Upside down. What's the 5 do? Let's do that together. Use your hands. What is that 5 going to do? Brianna's right. Make it taller. Yeah. The 5 being on the outside makes this graph 5 times taller, but it flips it. So I'm going to maybe sketch that like, I don't know, like this. I'm not even sure that's 5 times taller, actually. Might need to be even more than that. That makes sense. I've made this a very tall graph. Like this point right here at 1 should now go through 3, I guess. And this point right here at 2 should now go through 6. I wasn't perfect, but it's roughly right. That makes sense. And then last 2 things, I can do this because I can select this thing. The -1 means to move this thing that way over 1. And then the -2 means to drop this guy down to about there. I'll just put a little dot right there. Where does this graph start? Where is this point right here? Does that make sense? Like this point where the graph starts? 1 and -2. Yeah. Which is this 1 right here, but ignore the negative, flip that. And it's this -2 right here. So domain and range real quick. Domain means that x has to be greater than or equal to 1, or we'd write that as 1 infinity. guess see the change here though? The way this notation works is you always start with the lowest number and go to the highest number. So don't write this one as -2 to -infinity because that's the wrong order. You have to start as low as you can go and tell me how high you can go. And if you tried to write it like this, you're starting at -2 and then you're getting lower. That's not how this works. The lowest thing you can reach is -infinity. And the biggest number you will ever get is -2. So I guess you could write this as x is less than -2. What's that? Good point. Thank you.
But it still means that you're going from -2 to negative.
Right, but just this notation here always goes low to high. That's all. Is that good? That makes sense? Okay, moving on. I think I threw a slide in here just to illustrate that if you threw a 2 in front of this thing, it makes it taller. This is the normal graph. If you throw like a 0.2 in front of it, it would like squish it downwards. I think you guys know this stuff. Here's a summary slide that kind of talks about domains and ranges. Let's move past that. What is the difference between these two functions? What is the first one doing? What's the 3 in front of you? 3 times taller. Yeah, it would be fair to say that this graph right here is 3 times taller. What about this one here? Sure, that'll work. So can I say that this one would be 9 times thinner? Does that make sense? Like we're squishing it in a 1/9, whereas this one here is 3 times taller. Okay, I want to graph both of these things on a calculator now. So make one of them be a 3, then square root your x. And then make the other one be the square root, and let's make it 9x. And I'm just going to bold the second one just so I can see them. Okay, so maybe watch my calculator. Here is the first one. That's 3 times taller. Here's the second one. It's 9 times thinner. What do you notice? They're the same. Yeah. In this particular example I showed you here, if I took a cube, I'm just going to throw on just a regular graph just for comparison here. Just the regular square root x graph. If I made it taller, see whether this makes sense. This point here is now up there. This point is now up there. This point is up there. This point is up there. This point is up there. Taller makes sense, I think. But thinner actually is the exact same thing. I'm going to take this point right here, and I'm going to shove it into there. I'm going to take this point right there and shove it into there. And way off the graph, this point over here got shoved into there. In this particular function, taller is thinner, actually. They can work the same way. It's just you use a different number. And maybe this would make sense. Doesn't 9 actually square root to 3? Which I think maybe you probably noticed at some point, right? So the point I want to make on this one here is that you could call this one a taller graph, or you could call this a thinner graph. Both would actually be valid, because it's doing the same thing either way. Okay, here's a challenging question. We have a radical function that goes through the points 0, 0, 1, 2, and 4, 4. We're going to try to write a function that can do this. I'm just going to graph this thing here. 0, 0 would be right here. 1, 2 would be right about there, I guess. And 4, 4 would be over here. Kind of gets my start here. In order to write a function for a square root graph, unfortunately, is way trickier than writing a function for polynomials. When I ask you guys to write a function for polynomials, we write out the roots, we throw an a value in front, and we plug in some numbers to find that a value. To write a function for a square root graph, I don't have a trick that works. really the best thing I can do is say, well, think of what square roots are supposed to do. If I plug in 0, is it supposed to square root and give you 0? It is. If I plug in 1, is it supposed to square root and give you 2? Okay, that's odd. It's like the graph has been moved up by 1 almost. Because it was supposed to square root and give you 1, but now it's giving you 2. Well, okay, but actually it isn't plus 1 though. Because plus 1 means that this one would not be at 0, 0. It would be up 1. Brad's actually figured it out already. This graph is double what it's supposed to be. What is 4 supposed to square root to give you? But now it's up to 4 instead. So this one is 1 higher than it's supposed to be. This one is 2 higher than it's supposed to be. So we're not actually adding 1 to it, we're actually doubling the graph. This is the graph of y equals double the square root of x. Does that make sense? That's one of the equations I could have written. What's the other one? That's the other equation you could have written. Y. Yeah, or I guess working backwards, the 2 can go inside the square root sign and become a 4. Does that make sense? You may get asked a question where they give you some random points and you get asked to write a graph about it. Like I said, it's not the easiest thing in the world to do because there's not like a nice formula. So the advice I'd give is consider the x and y values and how they square root. And what you may need to do is like just throw a 2 in front. Or you might actually just need to put a -1 afterwards. But this makes it a bit more of a challenge than you're used to. Okay, are we almost done? Yeah, 2 more things here, then we'll call it a day. We also should be able to solve for x. Do you guys remember doing this last year, the idea of how to like solve an equation that has x's in it? Okay. One thing you could do is you could type this into your graphing calculator, make that equal to y1. You also could make this equal to y2, and you could find where they intersect. That would work. But because I think you guys are probably pretty good at that, I'd rather just do a couple of examples of solving algebra by hand as well. So let's do this one over here. To solve any sort of square root graph, get the square root by itself. So add the 2. So then you get the square root of x minus 3, and that's going to equal x plus 2. Good, yeah, to get rid of a square root, you square. But that means that you have to square the whole other side.
Yeah, x plus 2 on one side. X plus 2 squared.
So x plus 2 squared, by the way, means you actually have to FOIL it. So it means you get x squared plus 4x plus 4. It's quadratic, so subtract x from both sides, add 3 to both sides. You're going to get 0 equals x squared plus 3x plus 7. And then use the quadratic formula, which I won't bother doing. But you guys would be able to. That being said, it may just be easier to type this into your graphing calculator as y1, type this into your graphing calculator as y2, and see where they intersect, because that would also work. Let's just try one more just to make sure you guys know the basics of how to do it algebraically again. Let's do this guy down here.
Can we do that big one on top?
This one right here?
Yeah.
Oh, okay. That one actually is not as hard as you think it is. It looks intimidating. To get the square root by itself, first let's divide by -3. So that guy's gone. 9 over -3 is just -3. So would it be okay if I just kind of did this and made that a -3 right there?
So then would you still square the square root?
Yeah, square the square root. So squaring the square root makes it go away. So you get 3x over 4. And what happens when you square root -3? Positive 9. Times up the 4. That gives you 36. And then divide by 3, divide by 3. X is 12. I feel pretty comfortable you guys have these skills. I mean, we haven't worked on them a ton recently, but I know we've done this at some point. Let's just do, I guess let's do this guy over here. I have a trick for this guy over here. How could I solve this one? Square both sides. Okay, so this guy becomes x plus 2 and an extra x plus 2. I'm actually not going to FOIL it, because there was a purpose behind this one, I think. What happens when I square this guy over here? It gives me just 5x plus 2, and I think Sean just noticed you can cancel. So x plus 2 equals 5, subtract 2, x equals 3. Yeah. Check your work. 3 plus 2 right here would give you 5. Times it by 5 would give you 25. And square root it would get you back to 5. And 3 plus 2 is 5. Ta-da. So, anyways, I just want to review the fact that like you can do this algebraically. I don't know that you ever for sure have to, but it's a good skill to possess at some point, right? But you could make this equal to y1, this equal to y2, and you could find where they cross. Oh, wait, last thing, and then we'll stop. You are likely going to be given a word problem. Now, I do not know where the word problem is going to exist in the non-polynomial function section, but it will probably be either in the square root section or in the fraction section or in the exponents and logarithm section. But somewhere in there, they're going to give you a word problem. It's very likely. It's hard for me to prepare you for word problems because I have no idea what they're going to be about. But chances are what they're going to do is they're going to give you an equation. And the equation will be long and convoluted and look something like this. So it actually has some physics overlap on this particular one. This one, if I remember correctly, is basically the speed of sound changes depending on the temperature. If it's hotter or colder, sound can travel slightly faster. I taught a few of you guys physics. Do you guys remember what the speed of sound approximately was? Yeah, 330, 340-ish meters per second. But apparently, if we change the temperature, it can change the speed. Does this number right here ring any bells for you guys from chemistry? Yeah, that's how you convert Celsius to Kelvins. 273.15 is a Celsius Kelvin conversion. So here's the good news, though. We can use our graphing calculators. So let's plug this in our graphing calculator to work on it. Just make sure you're very careful with how all of this stuff works. So we have a 331.3. Then I have to square root. I have an older calculator than some of you guys, so like I'm going to open up a bracket here. I think some of your calculators, you just put the square root sign underneath it. And then I'm going to go 1 plus, and then you see how this guy right here is a fraction? I'm going to myself use an extra like bracket for that fraction so that I get x over 273.15. And then I got a double bracket to finish. Let me know if you have issues typing that in. Because now I'm going to graph this thing. And get nothing. Yeah, that's kind of the point behind this question here. Is I want to kind of try to show you guys, okay, in order to figure this out, part A was let's figure out the domain and range. But we got to try to figure out where this graph is, because clearly this graph is not going there. So here's a tip. Go to your table. And yeah, right off the bat, it's up in the 300 range. Does that make sense? Which actually, doesn't that make sense? What does this 331.3 do to a graph? It makes it really tall. So let's make our window. I'm going to suggest we don't really need low numbers. So maybe let's make it start at 300 maybe. No, that's wrong. Not that 300. This one I want to start at 300. And maybe have it go to, I don't know, 400. I'm just messing around to start with here. Does that make sense? At least now I get to see the graph. Does that make sense so far? Okay, what is a square root graph supposed to look like, though? It's supposed to start on a dime. I should actually be able to see the point where the graph just starts. And clearly that is not here. It's got to be way back there somewhere. Anybody have any idea how far back it would be?
73.
Good. And here's a little bit of logic you can maybe use to help solve this problem. The stuff under the square root sign cannot, well, no, not 1, 0 actually. The stuff under the square root sign cannot get any lower than 0. So in a way, what I need to do is I need to take 1 plus t over 273.15, and I need to make that equal to 0. to find where it would start. So then if I minus 1 and I minus 1, it would be t over 273.15 equals negative 1. And if I times this guy up over there, it means that the lowest temperature I should be able to get is negative 273.15. And I taught all of you chemistry. You probably knew that at some point, that that's the lowest temperature you should get. So for my window here, I'm going to make it go as low as negative 300 maybe. Maybe I need to go a little bit lower than 300 now. I'm just going to mess around with this a little bit now. Let's make it go as low as 0. Let's make this go to positive 300 maybe, just so I can get some. Here, now I've got a graph that looks a little more like a square root. So just in case you want my window sizes, I went negative 300 to 300. And I went 0 to 400. So finally, I have a point right here where the graph literally just starts. If I were to sketch this graph, like if I was asked to sketch this graph, I guess this kind of works. That point right there apparently would be negative 273.15, comma something. That makes sense? What would the other coordinate of that point be? Anybody know? It is actually. If I plugged in negative 273.15 right here, this would all give me negative 1. When you do 1 plus negative 1, it would all go away, making it 0. And the fact that you multiplied 0 by 331.3 means that that's the lowest point you get. If I were to go, like second calculate the value and type in negative 273.15, it will actually tell me that y equals 0. Now, I'm not sure about some of your newer calculators, but my calculator right here does not make it appear like this graph actually is starting right there at 0. Does that make sense? Like, it sure appears like it's starting up here. This has to do with pixel size. This graph is very steeply kind of shutting off right here. The point I want to make then is you got to be really careful with square roots. You cannot find this point right here using some sort of calculator buttons. Does that make sense? You have to find this starting point right here using some logic as to how your graph equation works. Because like if you try tracing this thing, you like try to find where the graph looks like it stops, that is not the place where the graph stops. Does that make sense? Which kind of sucks, because it means that you need to be able to algebraically figure out how this graph is working. I guess what that would mean, though, and maybe this makes sense, is that if you could make something be at absolute 0, sound would not move. Sound waves would no longer have a medium to move through because it's so freezing cold that they can't travel. Okay, I want to speed up here. Domain and range, then. Domain. Anybody? X is greater than or equal to negative 273.15. So that would be negative 273.15 with a bracket, infinity. Range? 0, yeah, y was greater than 0. Again, does that make sense? The graph doesn't look like it starts at 0, but it does. Make sure you're so careful on that. How can I find the speed of sound at 20 degrees Celsius? What do I do? What calculator tools do I use? Second, calculate the value when x is 20. How do I determine the temperature required for the sound to be 295? Y equals 295. Graph the thing and find where it intersects. Still with me? Okay. And this one's kind of mean. It said change the entire radical into a mixed radical. That one's actually the hardest one. So let's do that, and then we'll take, I know it's almost into class, but we'll take a little bit of a break, I guess, then, because I'm done finally. Okay, so here's my equation. It was 331.3. And then it was 1 plus t over 273.15. Do you guys remember how to work with fractions? How do I put these two fractions together? What do we need? Okay, so the common denominator is going to need to be 273.15. So I'm going to keep the 331.3 out front, and I'm going to make this 273.15 over 273.15. And maybe I'll just go right to adding t right here. That makes sense so far? Okay. And then what I could do is I could take that 331.3, and the trick I want to show you here, see whether this makes sense, is I could write this as 1 over 273.15 bracket 273.15 plus t. You guys see how I kind of factored the bottom out front, but I made it a fraction?
Is that those two the same thing?
Like from here to here?
Yeah.
Yes. So like what I've done is I've taken the bottom of this thing right here and I've kind of pulled it out front, and I wrote it as a 1 over top of that. And then this stuff right here is left. So I mean, even if I refoiled it, if I did this times this, you'd get 1. And if you did this times t, well, you just have t over top of that. This number, although it's not a square rootable number, can now actually come out front of the square root sign. Because I factored it out, right? If this number was 4, we'd put a 2 outside. If this number was 9, we'd put a 3 outside. Does that make sense? So I know this is ugly, but we could take the square root of 1 over 273.15, and that number can now come on the outside. And it would then times by the 331.3 that's out front there. So another way of writing this would be 20.04568 273.15 plus t. This would be the same equation. Should I show that one more time?
Yeah, I kind of got lost like how you did.
Okay. So like, you know how if I gave you like the square root of 9x, you could make that 3 root x? It's because 9 square roots to give you that 3. Well, I have a number right here. It's an ugly decimal number, right? But I have a number right here. I'm going to pull it out front. But to pull it out front, I have to pull the square rooted version of it out front. So in my calculator, I took 1 over 273.15, this guy right here, and I square rooted it. And now this number right here should now go out front. But since there's already a 331.3 sitting out front, I times it by that number. So now the new number sitting out front is now basically 20. And this would be, I've now simplified the expression by changing the entire radical into a mixed radical by pulling the number from inside outside. It wasn't all really purposeful. I just wanted to show you that skill. It's probably going to feel for the next unit like I'm just teaching you a bunch of random mishmash of skills. Because to be honest, I kind of am. I'm just teaching you a whole bunch of little weird things here and there. Like here's what the graph looks like, and here's an equation we can use the graph. I'm trying to find purposeful examples that will help you solve whatever question they ask you. Because I don't know what question they're going to ask you. The outcome that I'm supposed to teach you is that students understand how radical functions work. It's so vague. It's like students need to know what radicals are. It's like, well, you know what they are. The question is like, what are they going to ask you to do with them? Does that make sense? So today, kind of a random thing. Like we talked about a word equation. We talked about how to solve them by hand if we have to. We talked about if I gave you some points, could you make a graph? We talked about how like the 3 on the outside is like the 9 on the inside. We talked about domains and ranges and stuff like that. So, like I said, if it feels like I'm just teaching you a bunch of random stuff, to some degree I kind of am. The overriding topic, though, is can you work with square roots? Any questions? Okay, cool. We'll stop there.